Hi, in this video, I will be showing you problem number 11 of chapter 11, section 5. Test the series for convergence or divergence. Sigma n varying from 1 through infinity, negative 1 to the power of n plus 1 times n square over n cube plus 6. We notice that this series is an alternating series. Because of the fact that we have negative 1 to the power n plus 1 in front of the positive terms. Negative 1 to the power n plus 1 changes sign alternatively. So it is positive when n equal to 1 and then negative when n equal to 2 and so on. So it is an alternating series. So it makes sense to apply the alternating series test. So as we did in the previous problem, the alternating series test is quoted here. If the alternating series is b1 minus b2 plus b3 and so on with the bn more than 0, and if it satisfies the two conditions, one of which is the sequence bn is decreasing, bn plus 1 less than or equal to bn for all n, which means the sequence is decreasing, and the limit of the nth term in the bn's equal to 0. Limit of bn as n approaching infinity equal to 0, then the series is convergent. So that is the rule we are going to apply in this problem. So we will write the given series, which is an alternating series, like the way we normally write sigma n varying from 1 to infinity negative in this form. So it is sigma n varying from 1 through infinity, negative 1 to the power n plus 1, n square over n cube plus 6 is something like sigma n varying from 1 through infinity, negative 1 to the power n plus 1 bn, where bn is the positive part of each term, n cube plus 6. For n varying from 1 through infinity, this is definitely positive for n more than or equal to 1. So it does satisfy that bn more than or equal to 0, more than 0 condition, and then we have to prove it is a decreasing sequence. Bn is a decreasing sequence. Sometimes it's an obvious condition like we did in the previous problem, that is 11, 5, 5. Problem number 5 of 11, 5 was easy to prove the decreasing condition. In this case, it's not that obvious because it involves n on top, not just a constant. So we are going to apply the increasing decreasing test that we did earlier to prove that sequence is decreasing. So we can consider the corresponding relating function. Let's consider the function which is x square over x cube plus 6, which is where n is replaced by x. This is known as a relating function. So we'll consider the derivative of this function is u over v type, so quotient rule is applied. This denominator times derivative of numerator minus numerator times derivative of denominator over denominator square. So here we can actually take the x out. X is a common factor in these two. Then we can write inside 2x cube, 2 times 6, that is a 12, minus x is taken out, that is 3 x cube. Divided by x cube plus 6 the whole square. So now it would be x times 12 minus x cube divided by x cube plus 6 the whole square. So x and x cube plus 6 the whole square, the denominator is always positive. In the context of the problem, we are going to only consider the decreasing condition a decreasing condition for all n, meaning that starting from 1 onwards or eventually also. So it's only starting only from x equal to 1 here, so it doesn't matter here. This 1 is going to be always positive, x is positive, x cube plus 6 the whole square is positive. So the sign of f prime x depends only on the sign of 12 minus x cube. So 12 minus x cube will be negative. If that has to be negative, then 12 must be less than x cube. Or x cube is more than 12, or x is more than cube root of 12. So if you find out what cube root of 12 is, it's approximately 2.29. So whenever x is more than or equal to 3, f prime x is going to be less than 0. Or we can say f of x is decreasing for x more than or equal to 3. So, which eventually proves condition 1. So, bn plus 1 less than or equal to bn whenever n is more than or equal to 3, or eventually. So, the next is, this is pretty much condition 1 that is stated in the theorem, in the rule, alternating series test. And then we have to consider the second requirement, which is limit as n approaching infinity of bn. So limit n approaching infinity of n square divided by n cube plus 6. So if we divide the numerator and the denominator by the highest exponent of the denominator, which is n cube, we get the numerator n square over n cube, that will be 1 over n, divided by n cube over n cube, that is 1, 6 over n cube. So limit as n approaching infinity, the denominator, this part is going to become 0, this part is going to become 0, so it is 0 over 1, which is equal to 0, which is pretty much condition 2. This is pretty much condition 2 of the alternating series test. So we established condition 1, we established also condition 2. So by alternating series test, the given series converges. Negative 1 to the power of n plus 1 times n square over n cube plus 6, this alternating series converges. So this is the conclusion part. So in these problems, keep in mind, you just cannot say the series converges or diverges. It doesn't, you have to actually establish all the requirements of the test that you are using. You have to state the test. You have to also make sure that the conditions that are needed to be, the required conditions in the test are proved. So that's what we did. Condition 1 we proved, and then condition 2 also we proved. Condition 1 is showing that the sequence is decreasing eventually, and then condition 2 is to show that the limit of the nth term equal to 0. Then you can say by conclusion of alternating series test, the given series converges. Hope this video helps.